Gdansk. He's a world expert for quantum information theory, very well known for the Pawel Horodecki criterion, which has been shown here in a few talks already, which he established together with his father and his brother. And we are very grateful to have him here today. So please, Pawel.
Yeah. Okay. Thank you very much. Thank you. I would like to thank the organizer for the kind invitation, for the possibility to be here and to talk. This is the title of my talk is Testing Quantum Mechanics and Beyond. Could you hear me? Right? Okay, good. I mean, definitely on the internet they do hear me, but I'm not sure whether in the audience. Right. Okay. So here are collaborators and the funding agencies. So some of the papers that I will be, okay, something is right. It has some delay. Yep. So some of the papers I will refer to are here. This one is a special one that is kind of telling about different methodology. So that will be a last part of the talk, which I hope I will manage to cover. There are some papers that are, distantly related, but to those who are interested, also maybe they're worth looking. So the history, very well. The strange thing that bothered Einstein was that when you have the two particles that are entangled, then if the first photon gets projected, when it goes through the polarizer, suppose it passes the polarizer, the second one gets projected despite it didn't reach the measurement apparatus at all. So that was the thing that was bothering Einstein very, very much. So he said, well, maybe there is some better quantum than the theory than quantum. In such a theory, polarization of photons, would be already predetermined before reaching the polarizer. So that we call now local realism, which means that the locally single particle really has realistic property independently on the measurement. And the measurement only has a passive role of revealing, the properties, like, in our everyday life. So that was the essence of famous Bohr-Einstein controversy. And in 1935, Einstein has published, Einstein, Podolsky, and Rosen, they have published this paper when they tried to argue that this local realistic perspective is right. And the essential point of this was that if one may remotely predict some property of a given system without interaction with it, then it must have existed before. It must have existed before. So it's called EPR paradox, and it focused much attention, even you see in the newspaper at that time. So it was needed more than 30 years when John Bell came and said, okay, I know how to formalize Einstein's idea. So if a EPR argument were right, the quantum mechanics should satisfy some tests, and he has pointed out that they do not satisfy them. So, so the idea of Bell was the photon just has already predetermined answers for the setting of polarizer. We have two options of setting it here or there, like this or that. And suppose photon knows, okay, if they post polarizer like that, I would pass, which is +1. If they would make the second position, then I would be absorbed. So you may formally write it in the, in the table, which is the following. Whenever the polarization is, sorry, there should be 0 here, because this is the first, in quantum information, we start from 0, right? So the first position of the polarizer is 0, the second is 1. Sorry for me messing up the notation. So basically, this means that the conditional probability under this particular x, setting is one of being passed and 0 for being absorbed. Now you have second position. Okay, here they are already correct. So, so you have the second position, and there is conditional probability that if the polarizer is in this position, then conditional probability is 100% of being absorbed. Okay, so that means that even before reaching, the measurement area, photon knows already 100% what will happen with it. So you can put the same for the second photon. So you have conditional probabilities, and they are local, they are independent. So that this is deterministic and that one is deterministic, the second. So when you put them together, you have joint table, okay? You multiply the probabilities and you see the rectangle of ones, okay? And any local hidden variable model, actually, in this particular example, is if it's deterministic, it means it should be some rectangle of ones. It might be some different choices, okay? Either this one or maybe that one, but it should be single one in each of the blocks. Here again, I have 1 and 2. I'm sorry, it should be 0 and 1. Okay, so, but it may be that there's some extra, element of the theory of physics that we do not know. So it may be that in particular, run of experiment, there is something that determines whether this is this rectangle or that rectangle, okay, or some other one, but we don't know what is that. So instead of, really developing the deterministic theory as Einstein wanted, we just say we don't know it, so we put some variable that we have to average over. And here is an example. Suppose the nature, flips a hidden coin like heads and tails. So then it says, in one run, I would just force the photons to have this distribution, another one, that one, okay? So because we don't know what nature decided, we have to mix them together, okay? And we have the new table. And any table like this, which is a mixture of those rectangles with some weights, is called local hidden variable model, okay? So you may have more of them, you may mix them in, over this lambda with probabilities. So in general, you have this mixture. So this is a single table, okay, deterministic, designed in that way. And you mix over those lambdas, which is those different rectangles. And this is famous local hidden variable model by Bell. Okay. So obviously, and this is formalization of Einstein's idea. So that means that if really Einstein was right, then all the tables, all the probabilities, conditional probabilities there must have been produced by this mixing, which means, mixing rectangles of ones with some weights. And now, okay, and what happens if we have this experiment and we have plus and minuses passed or being absorbed, and we multiply the results, okay? So this is for the setting 2, you put here plus or minus depending on whether the photon is going through or is being absorbed. So over this, when you average this value over this statistics, okay, over this statistics. So you put here 0, 0, 0, 1, 1, 0, 1, and depending on the polarizers, you put it into this formula, okay? So you average over those probabilities, these values, okay? What you get is bounded by 2, and this is quite easy to find because in each single run, this is just plus minus with multiplication. So this is just back on the envelope calculation. However, when you look at this vector and you calculate quantum probabilities, this is the table. And the question was, can you simulate this table with this mixture of those rectangles of ones, right? Can you represent this table, okay, as a mixture, some probabilistic linear combination of those rectangles of ones? And actually you couldn't. Why? Because if you calculate quantum average, which means average over those probabilities is 2 square root 2. Okay, so it's clear that that table I showed you cannot be simulated by those local hidden variable model. Okay, so the important thing is that in general, this is for this particular state, but you may ask, well, what if I have some other state, quantum state? Okay, I may have even higher spins, I may have, angular momentum, whatever, right? So important thing is that in general, I may have mixed state. So in general, it's hard to calculate the maximum over the settings of this object. But for this particular inequality, it is known that no other quantum state can reach more than 2 square root 2. And this is called Zero-sum bound. And generally, zero-sum bound is any quantum value maximized over all quantum states. Okay. And this goes back to 1980. So in general, it's hard to calculate, but for general mixed two or pure whatever, 2 spin 1/2 particles, there is this formula that I have a special thing about it because I was undergrad and it was the first paper we wrote. My brother and me wrote with our father, Richard. So in general, we call zero-sum bound maximum what you can achieve over all possible quantum states. I mean, not only spin 1/2, but maybe angular momentum, whatever, right? So Bell discovery says that photon properties did not even existed before the experiment was performed. But this is under 3 assumptions. I will come to them later, but it's very important to remember them. One is space-like separation, which means that during performing the experiment, changing the settings should be so fast that a light signal couldn't carry the information about the change from one lab to another. The second is high efficiency of detectors. This is technical assumption that very much depends on particular Bell inequalities, so people are trying to optimize and so forth. Some of them are, good with one respect and hard with another because you have more settings. And the last one is, which is called free will assumption, which means that locally you have randomly performed the settings. And this is very important that this definitely the minimal assumption is that you have to assume somehow that this randomness is independent on all possible physics that decides about the source. So, why quantum information for quantum information was so important to consider Bell inequalities, because, it was known, this is a quantum feature, is that whenever you have state that is extremal, means kind of on the boundary, it cannot be represented as a convex combination of any other states, then if it carries correlations, these correlations are kind of monogamous. So that means that we had a very nice talk before, right? Saying, what is that? That means that there is a bound on possible correlation of Alice with Eve and Alice with Bob particles. So if this one is maximal, that the second one must be 0, and this one as well. So basically, this extremality of this guy leads to monogamy of correlations in a very, extremal sense. This is maximal correlations you can imagine, right? When you set in the X, Z direction, you always, the same settings as polarizers, you always have the same results. So this, in Bell inequality, saturation of 2 square root 2 certifies this state. So that's what is important. You may consider angular momentum, you may consider Fock space even. If you have 2 square root 2, it means that effectively this is two-dimensional subspaces are entangled, and there is some other extra Neumark, whatever extension whatsoever that is irrelevant. So that idea, the pioneering paper is by Arthur Eckert, and this means that those properties are guaranteed even if we don't know quantum degrees of freedom, okay? So that means that when you measure, you don't need to know what you measure. If only it's quantum, okay? That's a fundamental kind of importance of Bell inequality for cryptography, because you don't need to lock in your device even. So that's idea of device-independent cryptography. Technically, it was developed in this paper. So Arthur Ecker is here. Yes. So that's the famous paper. That was the first application of entanglement in information theory at all. So I think it was the most quoted paper from physics in computer science, at least for some time. So, but foundational character of Bell inequalities is that they do not depend on the theory they are supposed to test. They just look at the conditional probabilities as they are. They look at them as it's a black box, okay? They don't ask about physics behind it. So that was actually, I think, the reason, that the combined reasons for the Nobel Prize, in 2022. So that was for experiment with entangled photons, establishing the violating of Bell inequalities and pioneering quantum information science, including the experiment, the cryptographic experiment between two islands, Canary Islands. So let's ask about assumptions. So first, just philosophical question that we at some point we looked with Michał Eckstein, who is in the audience. So the assumptions of science, which is somehow hidden, but we assume it, even if we don't know it, it's somehow very deep in methodology. The whole of our philosophy of science is based on the assumption that one is free to perform an experiment. So any well-posed question to nature is supposed to be possible to be asked. And there is intuitive reason for that. So we analyze it in that paper. And there is some paradoxical aspect of that I'm not going to tell you about it. Just look at this paper if you are interested. But the intuitive reason that we kind of explained after Hawking and Ellis, in some sense, you always need a part of nature to be independent on the physical law that you are going to test or falsify, because otherwise you wouldn't test this law, because your test is part of the law. So you have to put, you somehow, if you test some law, you have to really have some part that, if you really want to test it fairly, I'm saying you may have some partial tests or pseudo tests. It's okay. But if you really fundamentally want to test it, you have to have some independence. So how does it look in the case of Bell inequalities? Well, as I told you, space-like separation, high enough efficiency. This is technical assumption. That is not, well, it's hard technically, but it's not fundamental. This has been circumvented quite recently. And this free will assumption, which means that we need to have local sources of random bits. So let's look for Bell inequality, how it looks like. So what is this mean value of this? Bell, you remember this B is now abbreviation for this A0, B0 plus A. That was in this Bell formula, okay? So you can rewrite it in this way. When this is the probabilities of measurement settings of Alice and Bob, okay? This is this black box, means this statistics that physics tell us, okay? Like this is this table that the particular model gives us. So condition upon the settings, and this object is score of the game, which means actually the outcome of the measurements, right? So in this case, it's A plus times B, which means the plus or minus, you multiply it. And here, Alice and Bob are supposed to independently put the settings. So 50-50, right? So any particular one should be 50-50. So, okay, so the crucial point is that when you assume this local hidden variable model, as Bell did, this is only true when the settings are independent on lambda. So the source doesn't know what Alice and Bob are going to do. If it knows, end of the story. If it knows partially, it may know partially. It may be that lambda knows something about X and Y, which means that there is a bias. It's not 50-50. It's not 50-50. You remember, this was 1/2 times 1/2, right? Now assume that it's not 50-50, it's kind of biased. So lambda knows that, well, there will be tendency, to one pair of settings than the other. Then there is some maximum is bigger than 2 and even more for bias high enough of this type. This is even bigger than quantum, So for this one, we can reproduce quantum perfectly. But if source knows more, then can even, simulate something weird. So lack of free will assumption implies that quantum value or even more can be reproduced by local hidden variable model. Okay, so that we should really be aware of that. I will tell you later why. This is foundational aspect. So the one important thing is that it's also behind the scene, but just let me mention that Alice and Bob settings must not be perfectly correlated with each other. There should be some uncertainty between Alice and Bob, some independence between Alice and Bob. This is extra assumption. And quite remarkably, there are Bell inequalities such that knowledge about Bob settings is more helpful than knowledge of the source about Alice settings. So there are some asymmetric Bell inequalities. That's we provided this in this paper, where really it matters, what source would know, what is the correlation of the hidden variable with particular, Alice and Bob. So the practical conclusion is for cryptography, for instance, that if the bias is too big, and suppose this lambda is what eavesdropper knows, then via lambda he or she may completely corrupt the cryptographic protocol, because he or she just prepares with this lambda, prepares the source, kind of expecting what would happen, and he or she knows what would happen. About foundational conclusion, okay, let's look once again. So what would be this free will assumption? Actually, we would need to have something ontic, which means some source of randomness of bits that are only correlated with its future. It means that it's before nobody could predict. So the correlation is only a future cone. So what people did, what was done actually in those papers that was credited with Nobel Prize. The idea was you take the photon, put to the detector. In some independent photon, you put on the beam splitter, and you then correlate with your settings. Okay, but this assumes that quantum mechanics is true; it's correct theory, right? Already. So, of course, there was this cascade of papers, and concluded by Alain Aspect, famous article closing the door on the Einstein-Bohr debate. But when you look from foundation science perspective, you can ask, is it okay from that perspective to just accept that? And of course it's not. This is this Baron-Münchhausen problem that to prove unpredictability of quantum mechanics in terms of correlations, you need to assume some randomness that is local. Unavoidable possibility of superdeterminism. So foundational conclusion is lambda above may represent some unknown source of determinants that makes epsilon equal 0. And we only proved randomness of correlations between the photons, assuming the local quantum randomness is fundamental, but it may not be true. So this is something hard that you know that in science you have limits that are really you cannot overcome. So first is you cannot prove that mathematics is consistent, Kurt Gödel, right? Second is you cannot prove that laws of physics are stationary. Meta-predictability, right? Newton's law. Would it follow or not? Okay, so always we just live with some assumptions. And given sequence is truly random, you never know it. I mean, it's mathematical proof, you couldn't prove it. So in school, that's the example that we gave, right? To students, okay, look at this, is it random or not? It looks fairly random, but it's expansion of pi. So it's very much deterministic, right? So, it's at the end of the story. So there are two ways of trying to move further. So one is you look at stars. So when you take the the photons that are, determined your settings. You may take them from very far, the stars that are very far apart. And that means that if there was some lambda that predetermined those photons, it must have been in a common path of the two stars. And sometimes this common path is quite a long time ago. Here it's, prior to Gutenberg invention, which is itself predates the publications of Newton Principia, right? So probably if his dropper has, if there was a one, is no longer alive. But foundational is still, it's like pushing the source of the fate to the past, not dismissing it. So then again, there is an end of the story, or can we just make a little step in this fight with determinism? Is there any chance? Okay, surprisingly, we can. Two minimal assumptions about nature. We just make two minimal assumptions. The first assumption is, which we kind of understand, this is this no signaling faster than light, which is formalized here. It is just saying minimal assumption about correlations in nature. Settings here cannot, in one lab, cannot change the statistic here. So this B, statistic of B shouldn't depend on whether here you have joystick on this position or in that position, right? Because you would have, you would violate the principle of relativity. You would get this causal paradoxes and so on, right? Grandfather paradox and so on. So this is the minimal assumption, and of course the mathematics how to formalize. If you trace over A, the marginal should be not dependent on X, and this the vice versa. If you trace sum over B, the margin shouldn't depend on Y. You don't know what are the physics of this. You say maybe there's some future physics, some quantum gravity whatsoever, but definitely it should satisfy those things. Okay, those assumptions. So it was analyzed from information point of view in this paper by these two people. So what is interesting that you can even imagine then that the eavesdropper is post-quantum. It only obeys this no signaling. And there is a paper that shows how to produce single bit approximately. There are technical problems, but in principle, just assuming the eavesdropper is super powerful, it means that he or she only is restricted by this no signaling rules, but we are restricted to quantum mechanics. So this paper is pioneering. There's some sequels. We also were working on it. This is a hard problem, but and probably some progress here can be done, right? But so the first assumption, our first assumption about physics is that correlation cannot go beyond this polytope of no signaling. Polytope described by the constraints I have shown you. Okay. So it turns out that quantum statistics is smaller. And here is the Bell set, that's table. Here are those rectangles of ones, okay? Here is quantum statistics, and I will show you the table that is beyond. So the first important thing is that the extremality no longer you cannot simulate the extremality in this bigger polytope by quantum. So there is problem with security. That's why security problems against super quantum adversary are so hard, because you cannot use the trick that you did in quantum mechanics, right? Extremality, they're end of the story. No, you cannot simulate these guys by quantum mechanics. The last, or not last minute, but last year result is, if you even allow Listen Bob to sequentially measure many times, okay? Still you can't, you have many outcomes, many settings, never ever. So there are some limitations. I mean, this eavesdropper is much more powerful. Here is an example of, so no signaling obeys monogamy of correlations like quantum mechanics for those guys, but it produces much stronger correlations. You can see that here is 2 square root 2, but with this table, which is no signaling means that the rows, when you sum this and that one, should get the same. All the rows, this and that, this and that, this and that should be the same. This and that, this. You see, it's always half, right? So it gets 4, much more than this. Okay. So this is called Popescu-Rothig or PR box. This is the notation. So the first assumption is this one. This is the minimal assumption, okay? We cannot go beyond this polytope with correlation. Whatever the physics will be in future, it shouldn't go outside of this polytope. And the second one is we want to go beyond this determinism. So we say, well, maybe there is no free will in the sense of full randomness, okay? Maybe we don't have, full free will. There is no source of that is perfectly random. But suppose there is some source, maybe primordial black holes, or that have a little bit of randomness that is unpredictable. So that means that is fundamental. Maybe quantum mechanics is not so random as we think, but maybe there is a little bias. So mathematically, you call it Santa-Fazirani source. So you have this bias, maybe very big. Conceptually, you can imagine that this physics of the source, say black hole or whatever, and deep physical level works like this coin with unwanted big bias, but still for that no physics can predict fully what will happen. So you remember that you may have even the two sources that mask each other. So if somebody uses this coin or that and doesn't tell you which one is used, you would see completely 50-50. But it may be very much biased because that person may use, to choose the coin, may use this, expansion of pi, okay? So you then never know. It looks like 50-50, but it's very much biased, but you don't know which way in particular run. So we assume that you have this type of, and there is a very interesting result saying that you can never improve this randomness. If this is very weak, it stays weak forever if you have classical world. Deterministic computer, just classical laws of physics. No go. You cannot improve it. Randomness was weak, will stay weak. So let's assume there's, once again, two assumptions. Physics satisfies no signaling. There is some ontic randomness, but very weak. We don't know. It's maybe there is such a thing. But this is, we assume here very big bias. So it means that, it is not what was before, like 50-50 or, like, I don't know, 70% versus 30%. This may be arbitrarily small. The question was, can we still, for any epsilon, however close to half, refute Einstein criticism? Can we amplify any randomness of this type? Okay, so instead of classical machinery, we put quantum laboratories, and we know already that we cannot use Bell inequality, right? You remember that, okay? Because then, if the epsilon, we want to have epsilon arbitrary high bias, right? But we know that if epsilon is bigger than 0.3, already you see 2 square root 2, but there is no violation of Bell inequality at all in deep sense, because this is a spurious violation, because it was reproduced by hidden variable model. So when it's Bell inequality, that would really refute you this, despite high bias, okay? This one doesn't, if you have a bias in epsilon, this one doesn't refute this, CHSA doesn't refute you this. Okay, so there are two questions. So first, there was 2012, Renner and Kolbeck said, yes, you can do it, but if bias is not very big, you can amplify, but you also need to have perfect measurements. And Gallego said, yes, you have to assume perfect measurements, no measurement error, and access to unbounded number of devices, then you can amplify arbitrary weak source, and you can violate Bell inequality. You can refute local rallies. So we solved this problem of being in still of fragility of noise and need of charybdis of unbounded technical resources. This is in this paper, and there is a sequel with 2 devices only. So this is with only Alice and Bob. Here we needed 4, but it's maybe more easy to show. So how is it possible, actually? What is the conclusion here? So there may be no ontic unpredictable in the universe, but if there is an arbitrary weak one, then the nature has already no choice. It must also admit the ontic unpredictable in its arbitrary strong form. Okay? So nature is kind of no-go. Either there's no, but if there is a very weak one, then somehow even those quantumness, even if we treat it phenomenologically, it boosts it up. So in that sense, I used to say that it seems it's more likely that there is some fundamental randomness, unpredictable nature than not. And so how to amplify it? The idea is, like this. In no signaling, there was a distance of the boundary to this no signaling set. You might approach it in the limit of infinite settings, but that's not comfortable because you have unbounded number of resources. The question was whether you have Bell inequality, whenever you have Bell inequality and quantum set such that it touches this. So you would need Bell inequality somehow that would certify this point. And there is a one actually. So for 4 photons, this is entangled state of entangled entanglement, it's called. So there is a measurement such that, in the Bell inequality, this is the Bell inequality written in the computer science language. Don't worry about it. This is bounded by 2 from below for any local realistic model, but it's 0 for quantum and it's 0 for no signaling. So somehow this is the way when the quantum mechanics touches this, whatever would be future physics. But the question is, can we see such a thing in particle physics? Because this is quite, this is 4-party object. Anyway, you can do this. You can prove that this is the technical, bound on the error, because the error depends on the epsilon. You have to, screen your error. When epsilon is small, you have really control very well your device. But in principle, you can violate inequality. You can amplify randomness. And the technicals, I will just skip them. There is some methodology behind it, martingale's theory and so on. Only the magicness, where the quantum magicness comes to play. So you have the source, and part of it you go through the Bell experiment. So there are settings and outcomes. Sorry for changing the notations. And part of it you put to the classical extractor. So what this quantum object does, this quantum particles do, whatever correlations were in this weak source of randomness, they become decorrelated. Quantum mechanics works as decorrelator, so you have some randomness very weak, another randomness that may be stronger, but it's completely decorrelated from this part. So you put it just to classical machine and it works. Okay? So the power of quantum mechanics is that it works as decorrelator here. This is exactly the point. And well, what are the sources of randomness? I mean, there's even a paper they were looking for the heart beating. And it is random, but it's very slow. Okay. Practical consequences are the following. I think it's very important in particle physics because the holy grail is just this changing of settings. In particles, you just have detectors that are, you don't change your settings, whatever they are. But in future, what is important is that even if you can change a little bit, only if you have very, very weak, maneuvers, there are some Bell inequalities that you could violate with the same status as all those famous papers. Okay? So that's something fundamental. Of course, technically it's hard. I mean, I imagine that tens of years we would need for that. But in principle, if one finds a method of changing some parameters, you can do it. So of course there are questions: can we find some partially, maybe not even the settings, POVMs whatsoever, just twisting a little bit, and the special Bell inequality. Okay, that's important. That there must be an inequality that kind of touches boundary, cannot be the one. And well, what about these points? Beyond quantumness at all. I mean, this object is something that it's not even particle physics. It would be something different physics. Okay, but always we can search for that. I mean, if you have some Bell inequality that gives you something above quantum, like 4 in the CHSH or 3.2 or whatever, above 2 square root 2, you have new physics that is not quantum at all. Important take-home message: quantum mechanics allow to violate some Bell inequalities even with arbitrary weak randomness. It also allows to amplify this randomness to maximum. Well, what if we can't assume that we are in a situation that, how to say it, it's technically difficult. It's technically very difficult, okay? Can we find weaker scenario? Well, can we put some extra assumptions that make it easier? So we assume that there is some post-quantum physics, there is some eavesdropper, but it's hard, to deal with this no signal in statistics, because the Bell inequality is difficult. Finding Bell inequality and testing the one that is touching, controlling the error, it's hard thing, okay? So can we find something similar, but under more relaxed assumptions? And here is an idea. So suppose we have, some physics that we don't know, like before, no signaling, but we have one promise, that one of the parties, say Alice, has a promise that her particle is just behaving quantumly and has, guaranteed the degree of freedom. So say Alice knows that she has polarization, photon with its polarization. Bob doesn't know, maybe there is this particle interacts with some other particles or some unknown, maybe dark matter whatsoever, eavesdropper as well. But we have this promise that Alice has guaranteed that in her lab, you have photon, not some strange particle, just photon with polarization. So you know the degree of freedom. So this is related to the concept of quantum steering that goes back to Schrödinger. What is the idea? The original Schrödinger considered that, but it was formalized in a modern way. And for mixed state, it was formalized in this paper. What is the idea? The idea is you look at this and you just put absorber here. So on the left-hand side, so now Bob, not Alice, but Bob is guaranteed to have photon. Okay, only Bob is guaranteed to have photon. Alice doesn't know what happens because maybe she doesn't look to the box. Okay, she doesn't look to the box. But in the boxes, formally she bought a box with absorber, okay? But maybe somehow switched it. Maybe there is some particle physics or post-quantum physics that's going on in there because she didn't look, okay? She assumed that this is like this, but there may be something that she doesn't know. But she assumed that this is like this, that the photon goes, is either absorbed here or there, so that means that either it's projected here or there. So Alice has results that are just probabilities, outcomes of the box, and Bob just still has this photon. So these are the results of the experiment. Alice measures, Bob doesn't measure. So there are probabilities and states. You may multiply states by probabilities. You have a table. Okay, you have a table, and this table is called quantum assemblage. Alice is not quantum. Alice just is, just black box. Bob is quantum photon. So this again a convex set. And no signaling, you sum them up and you get identity over 2 everywhere. For 3 parties, you have the same. You can take GZ state, famous GZ state. Alice and Bob measures. So Alice and Bob gets some probabilities. Charlie gets state. You have a table, and there is a question. So what is the local hidden variable model here? Okay, what is the idea? The idea is that Bob has pre-existing state independent of Alice settings. Okay, so that's before was 100% probability. Here is determined state. So here you have, instead of rectangle of ones, you have rectangle of states that are independent on the setting. For this setting, everywhere is the same. Okay. So there is an analog. The convex combination of those is just analog of local hidden variable model. So before we had this local hidden variable model, quantum no signaling. Here we have such a thing. So we have assemblage, which is this table. It may be like this, it may be like this. Then it's simulated by measurement of Alice and Bob's particle. And you have some objects that are no signaling, which means that this is the only condition. You have some table that satisfies this condition, that's all. So, relations between these two were not clear. If you are interested, you may look at this paper. We did it some time ago. some obvious expectations are not true, okay? That's just good to know, okay? But generally, when you look, before you had this picture, now you have that picture. It's not, it has some curve, structure because of quantumness, because Bob has quantum particles still, okay? So it's kind of smooth. The boundary here is smooth. The question is whether this is empty or not. We don't know it. So are there objects here? And are there any analogs of Bell inequalities? How they look like and so on. And they are easy. Well, I mean, in some cases, they're very easy. You will see it. So if you have only two parties, then this is empty. So quantum, you can quantumly simulate any no signaling objects at all. So this is not an interesting situation. But when you have three of them, then measuring quantum state reproduces the state that is essentially smaller as before in no signaling boxes than the set of all no signaling assemblages. So the set of all no signaling tables of states is bigger than what you can produce by quantum measurements from three-party object. This has been proven in this paper. And there is a Bell inequality. How the Bell inequality looks like here. You just have probabilities as before. You have some probabilities of settings, probabilities of Alice and Bob, and you have mean value of some observables on Bob's side. Okay, Bob has to measure something because he has this photon, and these are observables. You combine this, and you here get separation, okay, between the three. Before, it was no separation. Okay, here there is separation. Okay, and now the question, so there are objects. What is the conclusion? For three parties, there are objects that mathematical objects that look like they are no signaling, so principle physics doesn't forbid them, but nobody knows if there is any physics that can reproduce them. One particle is just physical, just quantum. Other comes from unknown physics, future physics maybe, okay? But definitely not from quantum mechanics. So that's a question. We generalized this idea on this paper. There's a question mark whether you can see such a thing in nature. And the other question was whether it can reproduce extremal point. And actually, by this measuring, so whether quantum mechanics touches this boundary as an extremal. You remember, no signaling was not possible, right? Question is whether it's possible here. So let's remind me, what is the entanglement between A and B? So for pure state, it's just when you have a product, when you don't have product wave function. Entanglement between BC and A again. This is not product with that. What is genuine entanglement? Genuine entanglement with any party with entangled with other two. Okay, that was in the case of concurrence that there were examples like this. So now what is the result? Our result is, this is in this paper. For any qubit genuinely entangled, not only quantum mechanics produce extremal, touches this boundary in an extremal way, but also you have a unique certification of the quantum state. So when you have this table, you immediately see that must have been stated, that this comes from. When you have this statistics on the touching the point, you know that what was the quantum state that it comes from. So here is the GHZ. The simplest example is GHZ state. So you have this assemblage. There is this inequality. This is maximum over hidden variable state, analog of Bell hidden variable model is 3.4. Now the observables that you put in this is just these projectors without weights. So this is very easy, this is really very easy measurement. And you get this, okay? There are many other options. I'm not going to tell more about it, just to tell you that in this way, even we have physics that you have a post-quantum eavesdropper from quantum gravity whatsoever. Under the little assumption, Bob really controls the degree of freedom of his photon. We can fight with cryptography with this post-quantum, whoever he or she is. Again, the questions: can we, in particle physics, by measurement, can we find something outside of quantum mechanics? Okay. whether we have any any new physics that is not even quantum, but of course, can we just test this inequality in quantum particles, in particle physics? Again, some freedom of choice is needed. Okay, last thing. Okay, I think I will, yeah. I will not skip it, but I will just tell you how much do I have? All right. And I think I started five after. Okay. Right. Okay. So, I told you something that is actually not true. Well, it's true, but when you assume Poincare symmetry or Lorentz symmetry of spacetime. So, this assumption about no signaling, it's always true when you have two parties, okay? But when you have three parties, no signaling is equivalent to that type of constraints only when you assume that the laws of physics are, fully relativistically covariant. So you might imagine the physical theory when what is covariant is point-to-point signaling, in the sense that, you never, when you have point-to-point, never cause is after the result. But still, this no signaling that is not true. This formalist, mathematical formalist is not true. Why? That was first considered for infinite speed in this paper. We considered this problem for a finite speed, and we found some strange consequences for information theory. So when you look, this is as I told you, the only information transfer is covariant, but the physics is not covariant. Here. So this is like in some reference frame you may have Alice and Bob that are so that the intersection of their cones is the future cone of Bob. So physics does not forbid faster than line tempering correlations without tempering local statistics. Why? Because tempering with correlations, if the intersection is here, doesn't allow you to signal faster than light in any reference frame whatsoever. Okay, because these guys together can see that something happened faster than light only if they are here. But here is in the future of Bob. So the result you can simulate by just sending some signal, even much slower than light. Okay, so that means that in particular in the flat Minkowski space, you may just drop the no signaling condition with respect to Bob. However, in special space-wide configuration. So what that would mean that the theory is somehow partially highly non-local. You might have some integration over some kernel or something. We don't know whether it's true that it has somewhere in physics in our universe, but still there is no-go in the sense of we call it relativistic causality. The top theory that would they just obey this. We got relativistic causality in the sense that this is the minimalistic assumption that you have to assume when you have your correlations in space-time. The theory may be crazy, but if it's put on the space-time, it must satisfy this. Okay, and okay, so there is some bigger set. Okay, it has now we put those space-time variables on the top of what was before. So for some space-time configuration, I didn't put this. I may tell you later. You may have stronger correlations. You even with those correlations you can solve some problems much better, but not cryptography. We checked with cryptography, and the first problem is first is whether you can see such correlations, but the second is in this theory the monogamy is lost, so extremality loses the power of security. Second, all standard cryptographic protocols fail, so you can always find the, say, two satellites that would corrupt any protocol whatsoever, okay? Known protocol that were used so far. We don't know, maybe there is some smart one, but we haven't. So we are investigating now here under this project. So that's all I wanted to say about correlations between particles, okay? So the take-home message is you can, from correlations, you can see whether, first, whether there is some physics beyond quantum. Second, you can prove that something is non-local, even you have very restricted randomness, very restricted tampering, with your measurement settings. Okay, so those are the most important two take-home messages. That from correlations, you can see whether there is some new physics or not. And even if you have the physics that is just quantum, you may violate Bell inequalities with very weak randomness, but you have to have smart Bell inequalities, the ones that touch the boundary. And if I have 2 minutes, maybe I would just tell you some idea. They're not the technical details. So from some everything here concerned complex system, bipartite, tripartite, n-partite, whatsoever. But there's a question: can you test quantum mechanics, like saying whether there is something beyond quantum mechanics, just looking at single system? Okay, I give you single particle. Okay. So the thing is like this: if you have a promise that the perfect information capacity of the system is given, like this is the maximal number of messages you can encode reversibly. For instance, for spin half, it's just 2. You can perfectly encode 2 messages and decode it perfectly, right? For bit, it's also 2. So this is what we call, this dimension of the information content. So in case of quantum qubit equals 2 and bit, okay, the same. Okay. But that may be some other theories you don't even know, right? Maybe some future theorists. Suppose you assume only this, okay? Maybe some other. And you consider the following idea. You just try to encode in your system two different information. So this is 1 bit, okay, belonging to 0 and 1. And there is another, so this is, say, I, this is J, belonging to 0 and 1. And you encode it in the state of your system. So basically, it depends on these two, okay? So the total state, how it looks like, it's just this sigma ij, which is your quantum, post-quantum, whatever, times something that is classical. So we call it, I call this sigma I, but this is just, this I. This is classical bit, okay? And this J. And suppose that we randomly pick up 0 and 1 and 0 and 1 randomly. So that means that you have sum over ij equals 0 or 1 over 4 here. Okay, so this is your total state of your system plus A and B that are classical. So you try to encode 2 different sets of data in one system, single system, okay? Now the question is there an inequality that is satisfied by both classical and quantum mechanics, but there might be some crazy theories that do not satisfy it? And actually it's very, this looks very easy. This is in this paper. Just a second, I just will tell you the idea. So the idea is like this, basically, that if you take the correlation, what you do then, you just measure. So eventually you measure two observables, okay? You measure X, you try to measure X and Y, okay? So basically the correlations between X and B and A and Y and B. So this is this is A and B. So basically this is the inequality. the inequality is here. So this is this content, this D, and inequality is this one. So the correlations between outcomes and inputs minus the redundancy, which means correlations between these two guys, okay? Because these two guys may be repeated somehow, may be correlated, right? So you have to, so this is the inequality that surprisingly, it's satisfied by both quantum and classical mechanics, but people considered a lot of crazy theories on mathematical ground. You know, there are those mathematicians that are considered cone theory, right? Because you may try to kind of extend quantum mechanics in terms of instead of projectors on von Neumann projectors, you put some objects from some cones, and then you may get correlations that are bigger than quantum. You may get some statistics that are not quantum, and people. D is this dimension. Sorry, maybe D is this dimension is the maximum number of information. Then you reversibly, perfectly encode in your particle. You put one of them and you just perfectly decode them. So you know, one interesting thing is there is a crazy theory. I will just tell you without details. Okay, there is a crazy. Okay. Interesting thing is that we can formalize this inequality in some case like some uncertainty relation, okay, with constraint, but this is not important. So, you know, okay, so here is like, this is the region that is quantum and classical. If you write it as an uncertainty relation, this is the region below you cannot go. But there are some theories that goes actually beyond this region. And one of them is super crazy, and this is what I told you. They have this cone of states and cone of effects and so on. There is some, and there is a theory that depends very much on the n, and if you have simulation with some number even, then you have violation of Zero-sum bound. You know, this is a serious thing, right? I mean, this is super crazy, right? But another and odd, you have other. Zero-sum bound is okay, but you have a super crazy thing as information is, because this D is equal to, if you consider perfect imprinting and outprinting. But when you take many of them and you imperfectly print, it turns out that on average, you get more than 2 messages. On average, so this is a super crazy thing, right? Anyway, our inequality immediately for all of them sees that something is wrong, right? This is definitely not quantum theory because it's violated for all n. So this is the end of the story. I mean, just conclusion for this part, the short part, last one, is the following. Single system quantitative principle possible in terms of bound on non-redundant information. So you have some bound on non-redundant information about input-output. Okay. It rules out many non-trivial post-quantum theories, so it can feel some post-quantum whatever physics is for a single system, but there's assumption about these needed. But this is not bad. You know why? Because if you evaluate this inequality in the lab, you have two options. This is kind of win-win. Either you just miss some degrees of freedom, okay? So you somehow you miss degrees of freedom in contact with apparatus, which means you couple with something you didn't know, or maybe just overlook some new quantum type physics, like maybe some particles are there. This is one option. Another option is, well, wait a minute, maybe this is something really crazy. Okay? But you know that you should if you violate, you definitely should look for something in your lab. Thank you very much for your attention.
Thank you very much, Pawel. Questions?
So thank you so much for the talk. There is something a little bit confused about when you talk about the minimal source of freedom. So you said that if the source is minimal and you have a deterministic world, there is no way in which you can make this source of randomness bigger, right?
When you have deterministic labs, yes. That's absolutely true, yes.
But then you say that if there is quantum instead, you can increase this source of randomness.
Yeah.
But now I have the question that's confusing me. So if the source of randomness is only small and only relegated to a part of the universe, like you say, like a primordial black hole and so on.
That we control.
Sorry?
The world that we control.
Yeah, but I mean, if the source of randomness is little, then the rest of the world, even if you assume quantum mechanics, is still deterministic or not?
No. That's a very good. Thank you very much, because this is a good point. Yes. Thank you for yeah. So the thing is like this. Where I have something to. Oh, this thing. So basically, it's like this. You have two options. One is the following. You have. This is this classical. This is like. You have here a weak randomness, epsilon weak. And everything else classical. Rest of the universe is classical, okay? Okay? Then you cannot amplify this. That's the end of the story. You cannot violate Bell inequalities at all. But you may have the situation when you have this epsilon with randomness, okay? And you have some part of this world, when you phenomenologically see quantum statistics, but phenomenologically, which means that, not under the assumption that it's a super strong, but phenomenologically. Okay? So we don't know what is, really below the ground of physics. But from this too, it follows that we can produce super strong randomness. This is the first thing, but also this thing was truly not phenomenologically. Non-local. Okay, so these are these two conclusions, right? So you have epsilon randomness, and you have something that looks like quantum mechanics in our labs, but you don't know what is at the bottom. But from these two, you first know that this really must have been truly, at least in some experiments. I'm telling you, this is a special experiment with this touching Bell inequalities. Otherwise, no. That they are really, truly on to the very foundations. Whatever would be the theory, quantum gravity, dark matter, it must have been non-local from the bottom, even it was simulated by something. And also from this epsilon that was very weak. Super weak means just epsilon close to zero. Okay. From the perspective of the rest, of the rest of the world.
Okay, thanks so much.
I had a quick question. Actually, we discussed the bound for like Bell inequality, where we have the Stillerson bound of 2 square root of 2.
Yes.
Which quantum mechanics cannot go beyond. If you go beyond, it means you're not in quantum mechanics. But then there is another limit of 4.
Yes.
Right? Can we have kind of a crazy theory that goes even beyond 4, or?
Well, yes and no. So in the case of CHSH, you cannot go above 4, definitely, because this algebraic bound. So you cannot, summing to 4 numbers that are modulus 1, you cannot get 4. But actually, the answer to your question is positive, and this is this super crazy thing. this thing. Yes. You couldn't get, you have some special inequalities, okay? That are, that you have some, Bell inequality touching this, so that here is bigger, but here is even bigger. Yep. And actually this paper, we consider, oh, right, you see, the communication complexity corresponds to some Bell inequality, actually. There is a theorem saying that any communication complexity problem in standard complexity problem under some assumptions, some Bell inequality. So here you have a gap, actually.
So what does it mean? I mean, if we go beyond 2 square root of 2, we break quantum mechanics. So what does it mean if you go beyond 4? I mean, what's
Oh, that means basically that you have that the results of this must have come from some theory that has some Bohmian flavor. It means that the correlations between 3 particles will vanish if this particle go away from some special region immediately. So that would be super, as I told you, that would be super crazy theory but in a special way, in the way that obviously this violates the Poincare invariance, right? Because obviously, but this still may happen in the way that the point-to-point signaling that you use, if you use those particles to signal just classical information, that would be invariant. Okay, that wouldn't violate this causality things.
Okay. Okay, I don't see any other questions, so we can thank Pawel again.